Hello, chemistry students. Today we're going to be performing our analysis of freezing point depression experiment. In this laboratory, we're going to verify experimentally that colligative properties depend on the number of solute particles and not on the solute's identity, and we're going to perform a detailed analysis of the freezing point depression of cyclohexane. Let's get started. For part A of this experiment, we're going to be confirming the nature of colligative properties. The first chemical we're going to be using is urea. The molecular weight of urea is 60.06 grams per mole. And we first need to fill our styrofoam cup halfway full with ice. And we then need to determine the initial temperature of the ice in our styrofoam cup. The initial temperature of the ice inside of our styrofoam cup is 0.2 degrees Celsius. We next need to weigh out approximately 1.8 grams of urea. And so we will be using 1.8031 grams of urea. We will now add our 1.8 grams of urea to the cup and stir using a spatula until all of the urea has been dissolved in the ice. And we will record the lowest temperature of the mixture. The lowest temperature reached by the urea and ice mixture is -3.2 degrees Celsius. We will now repeat the procedure using glucose as our chemical. The molecular weight of the glucose is 198.17 grams per mole. So we first need to fill our styrofoam cup up halfway full with ice. And we need to record the initial temperature of the ice in our styrofoam cup. The initial temperature of the ice inside of our styrofoam cup is 0.2 degrees Celsius. We next need to weigh out approximately 5.4 grams of glucose. The mass of glucose that we will be using is 5.4126 grams. We will next add our approximately 5.4 grams of glucose to the ice in our styrofoam cup, and we will stir to dissolve. The lowest temperature reached by the glucose and ice mixture is -2.1 degrees Celsius. We will now repeat the procedure one more time using sodium chloride as our chemical. The molecular weight of the sodium chloride is 58.44 grams per mole. So we need to fill our styrofoam cup halfway full with ice. And then record the initial temperature of the ice inside of our styrofoam cup. The initial temperature of the ice inside of our styrofoam cup is 0.2 degrees Celsius. We next need to weigh out approximately 0.9 grams of our sodium chloride. The mass of the sodium chloride that we will be using is 0.9014 grams. We will next add our sodium chloride to the ice in our styrofoam cup and stir until the sodium chloride has dissolved. And we will record the lowest temperature reached by the sodium chloride and ice mixture. The lowest temperature reached by the sodium chloride and ice mixture is -3.9 degrees Celsius. In part B of this experiment, we're going to determine the cooling curve of pure cyclohexane. In order to do this, we're first going to determine the mass of a 400 milliliter beaker and a test tube. The mass of our 400 milliliter beaker and test tube is 185.5266 grams. We next need to add 10 grams, or approximately 13 milliliters, of cyclohexane to our test tube. And we'll now determine the mass of our beaker, test tube, and the cyclohexane. The mass of our beaker, test tube, and cyclohexane is 195.5913 grams. We now need to wrap our 400 milliliter beaker with a paper towel and place it inside of a 600 milliliter beaker. In order to determine the cooling curve of the cyclohexane inside of our test tube, we're first going to create an ice bath using ice and 2 grams of sodium chloride salt, and we're going to make our ice bath inside of the 400 milliliter beaker. We're then going to insert a thermometer into the cyclohexane inside of our test tube, and we're going to lower the thermometer and test tube down into the ice bath. We will then start a timer and we will record the temperature at 20-second intervals. Once the cyclohexane solidifies, the temperature will remain virtually constant, and we'll continue collecting the data at 20-second intervals until the temperature begins to drop again, or typically after about 10 minutes. We are starting our timer as we insert our test tube containing the cyclohexane into our ice bath. You should now be able to determine the cooling curve of pure cyclohexane. This concludes part B of this experiment. In part C of this experiment, we're going to be determining the freezing point depression constant, or KF value, for cyclohexane. To do this, we need to weigh out approximately 0.3 grams of naphthalene. Naphthalene has a molecular weight of 128.17 grams per mole. And we're going to transfer that approximately 0.3 grams to the test tube that contains the cyclohexane that we used in part B of this experiment. The mass of naphthalene that we'll be dissolving in the cyclohexane inside of our test tube is 0.3100 grams. I've gone ahead and dissolved our naphthalene in our cyclohexane, so we're now going to set up the same apparatus that we used in part B of this experiment. And we're going to determine the freezing point of the solution in the same way that we did for the pure cyclohexane solvent. The initial temperature for our naphthalene plus cyclohexane mixture for part C of this experiment is 19.7 degrees Celsius. We will now lower our test tube containing the naphthalene and cyclohexane mixture and thermometer into our ice bath, which contains a mixture of ice and salt. We will record the temperature at 20-second intervals. You should now be able to determine the cooling curve for our solution of naphthalene and cyclohexane. This concludes part C of this experiment. In part D of this experiment, we're going to be determining the molar mass of an unknown solute. To do this, we're going to need a fresh 10-gram sample of cyclohexane. And so we need to determine the mass of a 400 milliliter beaker and a clean test tube. The mass of our beaker and test tube is 185.4469 grams. We'll next add 10 grams or approximately 13 milliliters of cyclohexane to our test tube. We'll now determine the mass of our beaker, test tube, and cyclohexane. The mass of our beaker, test tube, and cyclohexane is 195.4517 grams. We next need to measure out approximately 0.3 grams of our unknown solute. We'll be using unknown A, and we'll transfer our unknown solute to our test tube containing our cyclohexane. And we need to be sure that our solute is completely dissolved in our cyclohexane before proceeding. The mass of unknown A that we will be dissolving in our cyclohexane is 0.3089 grams. Our unknown solute has now completely dissolved in our cyclohexane, so we will now determine the freezing point of the solution in the same way that we did for the pure cyclohexane. The initial temperature of our unknown A plus cyclohexane mixture for part D of this experiment is 19.4 degrees Celsius. We will now lower our test tube containing the unknown A and cyclohexane mixture and thermometer into our ice bath, which contains a mixture of ice and salt, and we will record the temperature at 20-second intervals. You should now be able to determine the cooling curve of our solution and the molar mass of our unknown solute. This concludes part D of this experiment. Okay, students, you should now be able to calculate our freezing points, our freezing point depressions, and the molar mass of our unknown solute. This concludes our analysis of freezing point depression experiment. Thank you for joining me for this laboratory.